speaker this morning is Professor Alain. So Alain is going to tell us the second lecture of his Coxeter lecture to tell us about non-commutative geometry to absolute algebraic geometry. So please.
Okay, thank you. So I hope you can hear me because I might have voice problems, but with the microphone it should work fine. All right. So the plan today is the following. So as I explained in my first lecture, you know, non-commutative spaces have a very peculiar property which is not shared at all by ordinary spaces, which is that they have thermodynamics. And and moreover, as I mentioned in my first talk, you know, I mean, it would be crazy to decide one day I'm going to work on the Riemann hypothesis. I mean, that would be ridiculous. So, I mean, what I will explain first is how the Riemann zeta function entered in a very surprising manner in non-commutative geometry. And then I will explain the joint work with Katia Konsani, in which, if you want, we transform the non-commutative space that you get for the Riemann zeta function into a space which sort of can be explained in algebraic geometry in a more algebraic geometric language. And it uses topos theory, and it uses a new kind of coefficients, which at first are in the tropical geometry. And then what we found out with Katia by going much further is that in fact what we need is what I call in the title absolute algebraic geometry. So this is the plan of the lecture. And I mean, so in the first part, I will explain the non-commutative geometry origin of the things. And then in the second part, I will move to this absolute algebraic geometry. So, I mean, as I said in my first talk, you know, non-commutative spaces, they're amazing because they have this time evolution and it allows you to cool them down, for instance. Okay. So, but now you need good examples. And you need non-trivial examples, which are not type 2, because type 2 is static still. And when you consider discrete groups, when you use the usual stuff about discrete groups, their regular representation and so on, what you find, it's known since von Neumann, is a type 2 factor, because it has a finite trace. But the beauty of algebra is that there is room in algebra for the quotient of a group by a non-normal subgroup. You see, when you think about that, what you find is that in algebra, what you have when you have a group and a non-normal subgroup, you have an Ecke algebra. Okay, you have a convolution algebra of the cosets. And it turns out that if you take the simplest example, non-trivial example of a non-normal subgroup of a group, actually what you find is that, of course, you have the same story as for discrete groups, namely the regular representation, everything, but you find type 3. And this is what we did with Jean-Benoît Bost a long time ago. What we considered was the simplest example of a non-normal subgroup in a group, discrete. So what you do, you take the group of integers inside the rational number. This is normal because everything is commutative as additive groups. Okay, but you make it a little bit more subtle by taking the semi-direct product with the group of homothéties, okay, which is, if you want, the affine group. So you do that, and what do you get when you do that? You get, if you want, you get Ecke algebra, which is corresponding to the pair, if you want, of the affine group of the rational numbers, but you assume the A to be positive. I mean, this is better. And then what you have this non-normal subgroup, which is the one that you obtain by taking integral coefficients. All right. So, I mean, this gives you Ecke algebra, which you can compute with and so on, which is not very difficult to compute with. But what you find that because it gives you a type 3-1 factor, in fact, so it gives you a very non-trivial factor, gives you time evolution. You can restrict this time evolution to the C-star algebra of the group, okay? And what you can find then, you can compute the KMS states. Now, the KMS states, as I mentioned in my first talk, okay, they are defined by a condition, which is the condition of being an equilibrium state. I mean, and what happens is that, in general, what will happen when you cool down the system is that you will have a different set of KMS states, totally different. And but the interesting situation is one in which you have spontaneous symmetry breaking. In other words, where at a given temperature, which is fixed by the original regular representation, you have only one KMS state, okay, which is in this case of type 3.1. And when you cool the system down, namely when you increase the inverse temperature beta, what happens is that instead of having only one KMS state, you have a full family of extremal KMS states. Okay, you have a non-trivial compact space. And moreover, what is spontaneous symmetry breaking? Well, when you had only one KMS state, it had to be invariant under the symmetries of the system. But now, when you cool it down and there are many KMS states, what will happen is that any of these states will have a smaller symmetry group than the original KMS state. Okay, and this is what is called spontaneous symmetry breaking. So that's what we found with Bost a long time ago, and then we found that this system had remarkable arithmetic properties. So first of all, it had this phase transition with spontaneous symmetry breaking. Okay, and that one could say in very fancy terms what were the KMS beta states at lower temperature. Okay, and then they are parameterized by something that people who are very knowledgeable call Shimura variety of 0 dimensions. But what is really important was that there was symmetry breaking. So the symmetries of the system, they are easy to understand because they are the automorphisms of the group which is Q mod Z. And so, I mean, this is a certain Adélie group, which is the units in the group Z at, the projective limit of the group Z mod N Z. And what we had found with Jean-Benoît Bost is that, in fact, what was really interesting, if you want, is that somehow, if you want, when you evaluate the extreme KMS states on a natural subalgebra of the Eck algebra, which is the subalgebra where the coefficients are not complex numbers but rational, then you find that the value of these extremal KMS states are in the cyclotomic field, and in fact that they generate the cyclotomic extension of Q. And then you find that the class field theory isomorphism, which intertwines, if you want, the Adélic group with the Galois group of the cyclotomic extension, is exactly supplemented by the symmetry breaking phenomenon. So we were very pleased by this. You know, this was quite a pleasant interrelation between a quantum statistical mechanical system and number theory. But the place where the Riemann zeta function entered the scene is the next one. Namely, it is the fact that when you compute, physicists have a definition of what is a partition function. When you take this system and you compute its partition function, which depends on beta, you find the Riemann zeta function on the node. So you find that the partition function of the system is the Riemann zeta function evaluated at beta, this inverse temperature beta. Now, of course, we were very pleased with Jean-Benoît Bost when we found that, but and then in '96, I was invited in the anniversary of Zellberg, 70th anniversary of Zellberg. For this reason, I gave my talk, but then Zellberg came to me and he told me, you know, it's not clear that what you did will be related to Zeta or the zeros of Zeta and so on. So I started thinking about it. And about 1 week after I came back, I had understood that in fact, what was going on was not only that you have this partition function, but because when you have the partition function, you can only evaluate it at real values. You cannot look at it at complex values. So in fact, what I found rather quickly afterwards was two things. So what I found is that by looking at the non-commutative space, which is dictated to you by the BC system, what you find is you find a space which is of Adélic nature, which is non-commutative, because you have to divide, if you want, the Adels in general for a global field by the multiplicative group of the global field. But what I found, and this was really extremely pleasant, what I found is that, you see, there is a well-known formula which is called the Riemann-Weil explicit formula, and in which appears some very strange terms which are contributions from each place in a global field. Now, it turned out that the non-commutative space was giving a clear, very clear explanation for the terms which were appearing in the Weil formula. And the reason was simply computing the trace of the scaling in a local field now, because the local field was appearing for each place as a transverse geometry of the action of the ideal class group. So what happens is the following, is that when you compute the trace of the scaling, you are in fact, integrating the diagonal values of the Schwarz kernel that define the scaling, and you do a very elementary computation and you find exactly the wave term, which is 1 over the absolute value of u minus 1. Okay. So, I mean, this was very pleasant. And the second thing which was pleasant, if you want, so I had the impression really to understand the explicit formulas, I mean, in that way. And the second thing which was very pleasant was that, not only that, but the spectrum of zeta and of L functions, because they are all together in that, were appearing. It was appearing, but it was appearing in a very subtle manner. Because when you look at the Zellberg trace formula and all these formulas, the spectra which appear, they appear as point spectra, as emission spectra. But in the case of zeta, it couldn't appear as an emission spectrum. Why? Because in the explicit formula, you have a minus sign in front of the zeros of zeta. And this is how it appears. It appears as an absorption spectrum. So I will come back to that in my third lecture. And what I want to explain now is something, it's the start of the joint work with Katia Konsani, which is the following, which is that after all, in all this discussion, which I told you, there is a non-commutative space, but for people who don't know non-commutative geometry and so on, for them it doesn't mean much, okay? So what we did with Katia began to explain to me a lot of algebraic geometry and so on, and then, we worked together, and we started, if you want, we started understanding the algebraic geometry, which is behind the scene in this situation, okay? And that took a lot of work. And in order to understand, to have a mental picture of what we did, you need to know an analogy that André Weil was very keen to make, which is the analogy between the Rosetta Stone, which is behind the scene, okay, and a kind of trilingual, how to say, trilingual, very mysterious something which is given to us by mathematics. And what are, in this trilingual languages, what are the three languages? You see, in the Rosetta Stone, the lower part, which is in fact, more or less in Greek, is very understandable. The important thing in the Rosetta Stone is that the three texts tell you the same thing. So because they tell you the same thing, you have a way to try to decipher the other languages, okay? So here, the lower part is, in fact, the theory of Riemann surfaces, which we believe we understand extremely well, in the sense that, we have an algebraic and a transcendental approach to them and so on, and we understand a lot of things, okay? Now, what was found during the 20th century was an analog of the Riemann surfaces, which is, if you want, the theory of function fields. So the theory of global fields, which are of finite characteristic, and in which what you do algebraic geometry over a finite field, FQ. All right. And I mean, so much work was done in the 20th century that, if you want, most of the ingredients of the Riemann surface theory has been transposed in at least, for instance, the theory of curves over a finite field. And then you have the most mysterious part. And the most mysterious part is the integers and the Riemann zeta function. And so the first thing that we did with Katia was to understand how to translate one entry in the middle of the story, which is the Aceveil formula. So if you want the Aceveil formula, what does it tell you? It tells you that, in fact, the analog of the Riemann zeta function, when you look at function fields, has a very good interpretation in terms of a counting function. In other words, it's a generating function where what do you do? In fact, the only thing you are doing is to count the number of points of the curve you are looking at over the finite extension of FQ that you get by taking the finite field FQ to the n. Okay, so this is a finite number. You take these finite numbers, you write down the generating function, and here you are. You have the corresponding zeta function. That's, of course, extremely useful because it means that you have geometry at the end. and you can look, you can use a lot of stuff from geometry. Okay. So what we did with Katya was to do the same thing for the Riemann zeta function. And we were inspired, of course, by the fact that at that time, under the ideas of Manin and Soulet and so on, people had been trying to take a limit when q tends to 1. Namely, they had tried to do not geometry over fq, but to do geometry over f1, whatever it is. We shall see that we shall get very close to what it is, really. So people were trying to do that, and Soulet had defined a formula for the zeta function when q is equal to 1 as a limit formula of a certain expression. And if you want, he was taking an expression like that, but now because q is no longer an integer, the function n has to be a function which is defined for all positive real numbers. And so Soulet had defined a certain formula, but that formula which he had was okay for projective space. It was a very trivial calculation. But the problem with this formula was that when you look at the Riemann zeta function, the exponent which is here, which is n of 1 in the case of Soulet was considering, is equal to infinity. So this formula doesn't make sense because n of 1 is actually the Euler characteristic, and it has to be, in fact, minus infinity. Okay, so this formula doesn't make sense. So the first thing that we did with Katya was to transform this formula by taking the log of the two sides and by differentiating with respect to s, where you know, with respect to this variable in q to the minus s, we differentiate with respect to s. When you take the log and you differentiate with respect to s, this term disappears. And when you look at it more closely, what we found with Katya is that in fact it becomes a Riemann sum in a Riemann integral. Okay, so it's no longer a limit when q tends to 1, it's a Riemann integral. Because these are the sums, the partial sums in a Riemann integral. So of course with Katya we took the Riemann integral as a definition, okay? And so we defined, if you want, the limit when q goes to 1 by this formula. And so this term here is the logarithmic derivative of the zeta function you get from the counting n. And here, okay, I mean, you have this formula which corresponds to the exponent, if you want, in the Assay formula. So, and the problem that we set to resolve with Katya was to start to find the n, which will give you the full Riemann zeta function, namely the Riemann zeta function together with the Archimedean term. Okay, so we set out to do this calculation, and well, we went from surprises to surprises because we found a solution, but the solution is not a function n of u; it's a distribution. This distribution can be computed. It can be computed. It's given by using the von Mangold function and using a very tricky distribution which appears in the explicit formulas. But the beauty is that, in fact, it can also be rewritten in terms of the zeros of the Riemann zeta function by a formula of this type, where if you want, this sum makes sense, and this is a derivative in the sense of distributions. And then we were very puzzled with Katya because you know, it was important that somehow this distribution would be positive, because if it were not positive, it couldn't be naturally accepted as a counting function, of course. So it turns out that this distribution is positive. And here I plot for you the graph of the primitive of this distribution, the graph of this primitive of this distribution. And I mean, so you can see that the graph is increasing. But and in red here, what you have the approximation of this graph by taking the zeros of zeta up to the thousandth zero, so which approximate more and more this function. But the beauty is the following, and you don't see this on the graph. The beauty is that the primitive, so you see, it was like a headache because the counting function had to be positive, but its value at 1 had to be minus infinity. So how could this be? This looks like totally impossible. But in fact, what happens is the following. It's a very tricky thing. What happens is that it has a primitive. So it has a, it has a primitive. This primitive is increasing. But when you look at the primitive near the point q equals 1, you find that it shoots down to minus infinity. So, which means that its derivative is positive for q positive, But when you look at the value at 1, you differentiate. You take the value for close to 1 minus the value at 1. The value at 1 turns out to be finite. So when you take the difference between the value close to 1 and the value at 1 and you divide by the difference, you get minus infinity. And in fact, this minus infinity behaves exactly like the counting function of the zeros of zeta. So I mean, this convinced us completely that we had the right distribution. And then by using what I had shown, if you want, for the explicit formulas, we could combine that by saying that, in fact, this counting function is counting the number of fixed points of the Frobenius. It's not yet a Frobenius, it's just the scaling at this point. So at this point, it's just the action, if you want, of the ideal class group, or in this case, just of the scaling group on this space. So this space is the double quotient of the adels by the multiplicative group of Q and by the units in the projective completion of the Z mod NZ. So what happens then is the following. What happens is that at this point, what we had with Katia was a space which was still just understood as a non-commutative space, but we had the security that this space, by counting and by scaling, was giving the right answer. So that's where we stood at this point. Okay, but then we worked, and in fact, we began by realizing that this space, this double quotient, has a much simpler geometric interpretation. It is, in fact, if you think a little bit, it is the space of rank 1 subgroups of the real line. So by a rank 1 subgroup, I mean that a subgroup of the real line, so that any two elements of the group are commensurate. Namely, a multiple of one will be equal to a multiple of the other. Okay, so these groups are countable. And you might think that when you look at the set of these groups, it's an ordinary space. Forget it. It's a non-commutative space, okay, because it's a quotient which is ergodic and so on, which has a lot of properties. And then with Katia, we started trying to understand this space in algebraic geometric language. And what we found is that there is a way to do that. There is a geometric structure. And this geometric structure comes from by putting together two different notions. You need the notion of topos, of Grothendieck topos, and you need the notion of characteristic 1, which I will explain. And then in doing this way, we obtain the arithmetic site, but we also obtain, if you want, the Frobenius correspondences. And so this is what I want to explain, in a kind of visual manner. So what happens was the following. What happens is that in order to do this, we had to extend the ordinary, if you want, algebraic geometry tool, which is rings. We had to extend it to semi-rings. Now, you might very well ask the question, why could you justify for me that semi-rings are a natural thing? And the reason, in fact, is quite abstract and important. You see, the reason why rings are so important is that they are the endomorphisms of an object in any abelian category. That's really why they are so important. Now, it turns out that when you look at the axioms of an abelian category, first of all, I mean, you don't need to define an abelian category. You don't need to add a structure. The structure of addition of morphisms is automatic in an abelian category. It comes from the fact that the sum and the product are isomorphic naturally. Okay, so and it turns out that when you think about it, you find that when you do an abelian category, you add artificially the axiom that you have a minus sign. Okay, this is really an artificial axiom. This goes back to the book of MacLean on category theory. I mean, what I am telling, it's an exercise in MacLean. And so, in fact, what happens is that when you look at a semi-additive category, which is a category which has finite products and co-products, sorry, there is a co-product here, what you find out is that the endomorphisms of any object is a semi-ring. And the semi-ring is nothing complicated. You just drop the negative in the addition. Okay. And now if you open the book of André Weil on basic number theory, you will find that the book starts by a preliminary, which is a theorem telling you that the finite fields are fully classified by Galois. Okay. So Galois had one paper which was published when he was alive, and so you get the Galois field. Now, if you ask the same questions, but now you take semi-fields, all right, whose definition is obvious, there is only one additional guy. So in other words, the finite semi-fields are either finite fields or they are what is called the Boolean semi-field. Okay, and the Boolean semi-field is something you all know very, very, very well, because it's 0 and 1, and the only rule, which is non-obvious, is 1 plus 1 equals 1. And with Katia, we love to call that characteristic 1, because you see, it sits at this wonderful idea of the field with one element. But of course, if you write 1 equals 0, you are nowhere. Okay, and so the only way to get something is to write 1 plus 1 is 1. And when you do that, there is a marvelous result, which I think is in the book of Boland. So the marvelous result is the following. It tells you that if you take a semi-field of characteristic 1, so it satisfies 1 plus 1 is 1, okay, then for every integer n, you have an endomorphism of the semi-field, which is x goes to x to power n. So you don't have just one Frobenius. You have an action of the positive integers as a multiplicative monoid, okay, by this raising to power, okay. And so with Katia, what did we do? We defined an algebraic geometry object, which we call the arithmetic side. And what is it? It is, as you see here, you have not only one Frobenius, you have this family of Frobeni, which are parameterized by the multiplicative integers. So we defined a topos, and this topos is just given with, it's a topos associated to a small category. This small category has only one object, and it has endomorphisms, and they are parameterized by the semi-group and at cross, and cross, okay? That's it. This is the arithmetic side. It has a structure sheaf, and the structure sheaf is given by the only semi-field whose multiplicative group is cyclic of infinite order. You see, I mean, as you know, finite fields have the amazing property that their multiplicative group is cyclic. Now, there is only one semi-field whose multiplicative group is cyclic of infinite order, and this is a tropical semi-field, which is called Zmax. All right. So, and of course, it is a sheaf for this topos. Why? Because it has this action of the Frobenius. So it's a sheaf. Okay. So it's a sheaf. Now, the next thing, which is a beauty, is that in characteristic 1, you can have a semi-field whose automorphisms correspond to the ideal class group, to the quotient of the ideal class group by the component, by the easy part, I mean the Galois part, if you want. And what is this semi-field? It's a semi-field which has been used for a long time by many different branches of mathematics, by tropical geometry, of course, but also by the Russian school in dequantization and all that. I mean, it's a very, very important semi-field, which is what? It's just, if you want, the real numbers, but where what you do is you keep the product of real numbers, positive real numbers, and you replace the addition by the max, okay? And I mean, people in the Russian school and so on understood that this was a very important semi-field because it embodies the dequantization, the fact that you pass from quantum to classical, and it embodies also thermodynamics, in the sense that when you look for this semi-field R plus max, when you look at the analog of Fourier transform, this was done by Litvinov and Maslov and so on of the Russian school, you find that the Fourier transform is exactly given by the Legendre transform, which is really a beauty, because the Legendre transform is something very mysterious otherwise, but it becomes the Fourier transform in this sense. Now, the beauty for us, for Galois and for Katia and myself, was that, you know, we could compute the Galois group of this field in the sense of automorphisms of the semi-field over B. And we found that the Galois group is R plus star, namely the scaling group. And then, you know, the theorem is the following, is that when we take the points of the arithmetic side, the previous guy, over this semi-field, then we get on the nose the space which was coming from algebraic geometry, namely this double quotient. And moreover, the action of the scaling that was giving you the correct counting distribution is in fact identical with the Frobenius action. So you see, when you do algebraic geometry over a finite field, what you do is you take the points of the curve over an algebraic closure of the finite field, and then you look at the action of the Frobenius on these points, and then you count the number of fixed points and so on. So this is exactly what happens here. So what happens is that if you want the points of this object of algebraic geometry now, which is given by a topos and a semifield, over this guy, they form exactly this double quotient. And moreover, the action of the Frobenius automorphisms of this semifield is exactly the action of the delta group. So you have a beginning of a dictionary, you know, where you can begin to think of the, because there is nothing more productive in mathematics, of course, than an analogy, where you can transpose, you know, notions from one field to another. So here you have the start of an analogy, and the start so tells you that you have this arithmetic side, you have the structure shift. Okay, but what about the Frobenius correspondence? Because, you know, it's nice to have the Frobenius as an automorphisms of the coefficients, but you would like to have it also as a geometric notion on the space. And at first, this sounded totally impossible in the work with Katia. Why? Because this arithmetic side is totally countable. You see, you are given everything that you handle is countable. You have, you know, the multiplicative integers is countable. You have only 1 point. And then you take this Z max as coefficient. All of that is countable. So how on earth are you going to obtain an action of R plus star on this countable object? Okay? I mean, this sounded impossible. But in fact, the solution is geometric. And the solution, you should only remember this picture. So the solution came by looking at the square of the arithmetic side and thinking of a correspondence as subvarieties, as divisors, if you want, in the square, subvarieties of the square. And when you do that, you find that the square of the arithmetic side corresponds like to a two-dimensional, you know, integral lattice of this type. And that when you take a line of irrational slope, it will define actually the subvariety of the square. And this is in fact the Dedekind cut that define, if you want, the real numbers. I mean, here the positive real numbers. So what we found with Katia is that there were these Frobenius correspondences. There was a way to combine them, of course, like one combines correspondences. And what we found in a theorem is that the composition of correspondences was given by what you would expect, namely by the product of the corresponding scaling parameters. So if you want, we began to have something looking like geometry that could be used instead of the non-commutative space, I mean, the same space, but with a geometric structure. Now, much closer to algebraic geometry. And I mean, if you want, the motivation we had at that time with Katia was the fact that when you look at the proof of André Weil for the Riemann zeta function for curves, there is one proof which is amazingly natural and which is due to Matuk, Tate, and Grothendieck. And this proof is the following. You can really, at least, you know, you can understand what is going on in that proof. The idea is the following. In that proof, the idea is that you will look at the surface which is given by the square of the curve, and you will prove a Riemann-Roch formula in that square. So what we are doing with Katia was to look at the square, and in the square we could combine the Frobenius correspondences by, you know, taking coefficients, and then, okay, you know, what we wanted to have with Katia was the fact that if you want, the whole problem was equivalent to proving some negativity. And how do you prove this negativity in the case of Matuk, Tate, and Grothendieck? You prove this negativity by showing that the term you want to prove to be negative is in fact the index in the surface of the combination of the Frobenius correspondences. So that was our motivation. Okay, that was our motivation. But okay, so what we started doing with Katia, with this as motivation, is to do what people would do in algebraic geometry. Namely, you see, when you look at the curve over a finite field, you can look at the points of the curve over extensions of the finite field. But I mean, if you really want to do algebraic geometry, you have to work over an algebraically closed field. So you have to extend the curve to the algebraic closure of the field. And that's not the same thing, okay? So if you want, there is a nuance between taking the points of the curve over the algebraic closure and extending the curve to the algebraic closure. So what we did with Katya was to extend our object, our geometric object, to the Rmax, to these coefficients. And what do we found? Well, then we found something which by itself is already very striking, which is that in that case, after extension of scalar, the topos is a little more complicated than the dual of n cross. It's a topos which is a semi-direct product of the positive real numbers by the action of the integers. Something that all musicians know, because you know, it's frequencies, and you multiply frequency by 2, you get to the octave. You multiply by 3, you get to transposition. So it's something very, very concrete. It's a topos. Now, if you take the points of these topos and you compute them, you find exactly the same space, which is not surprising because it means that the points of the extended two scalars of the arithmetic side, they have to correspond to the points of the original one with coefficients there. Okay, so that's what we found. Okay, it's quite a non-trivial result, this result already, that the points give you this space. And so you have this fact, okay, of course, and then you have this canonical isomorphism. But what do you get out of it? Well, what you get out of it is a structure shift. So what you get out of this theorem, if you want, after extending scalars, you have also an extended structure shift. And this structure shift turns out to be something which is very familiar to people in tropical geometry, because it's something which is formed of functions which are it's formed of convex functions which are piecewise affine with integral slopes. That's what we found as the structure shift, and it's very, very intimately related to the localization of zeros of analytic functions by the Jensen formula. So I don't want to enter into that in detail, but I just want to mention it. And then you see we have now enhanced our geometric framework because we have passed to this algebraic closure. So what we have is the scaling side, we have the points over the thing, and we have now a structure shift which is much more interesting than before, because it's a shift of convex piecewise affine functions whose slopes is in the integers. And what we did with Katya at that point was to look at least the simplest case that we could handle. And the simplest case that we could handle were the periodic orbits. As I told you, the space, the non-commutative space we are dealing with is the space of rank 1 subgroups of R. This is the simplest way you can think of it, okay? Now, when you look at the rank 1 subgroups of R, it turns out that there is a place for each prime. What is the place for the prime P? The place for the prime P are those subgroups of rank 1, of this real line, which are formed, which are isomorphic to the group of integers divided by the power of P. Okay? Now, if you try to put such a group inside the real line, you will find that you can do that. You can do that, but not uniquely. And what you get is an orbit of length log P, which is exactly what you want for the explicit formulas. Okay. So if you want, when you look at the group of, yes, I think I'm doing well, yeah. So when you look at this group, abstract group, okay, of integers divided by the power of P, okay, you can put it, of course, in the real numbers. Let's take P equals 2, okay? So I can put it by taking all rational numbers which have a denominator power of 2 inside R. But I can also multiply that by a lambda. But if I multiply by lambda equals 2, nothing changes. So you see very well that I have an action of the scaling group divided by powers of P. And when you look at the scaling group in the right way, namely as an additive group, okay, you find that the length of this orbit is log P, which is essential, okay? So we do have this periodic orbit of length log P, okay? It's there in front of us, okay? So we have this periodic orbit. And now what we found with Katya is by looking at this periodic orbit and looking at the induced sheaf on it, namely as a structure sheaf. Then we found an object of tropical geometry, let's say, because it's a characteristic one, which is infinitely analogous to an elliptic curve. Okay, and that's what I want to briefly explain before I go further. So it's really exactly like the curve, elliptic curves in the sense of Jacobi. Remember that Jacobi has an understanding of elliptic curve by taking C cross divided by Q to the Z. Okay, here what we do, we take R plus star divided by P to the Z, P to the Z. Okay, which is, I mean, even simpler if you want. Okay, but you need to have the right geometry in order to handle it. And I mean, there the geometry is very, very simple. So it's this periodic orbit, sorry, it's this periodic orbit. So it has, if you want, the point, of course, which is this. It has a structure sheaf, which are the convex piecewise affine functions, whose slopes now belong to HP. HP is this group with denominators power P. And okay, so we have all the structure, and we can start computing. And you can define, once you have the structure sheaf, okay, you can define the rational functions. So you can do that. I mean, this is very easy. And you can define Cartier divisors. You know that the most conceptual definition of divisors is due to Cartier, and it's defined as by a quotient sheaf of two sheaves. Okay, you divide by a sheaf of invertible elements. So you can do that here. And what you find out is that the whole story is governed by the order of these piecewise affine functions. Okay, and so you can define then divisors, as I said. But the first thing that you remark, oh, and this was very striking, what we remarked with Katya from the start is that the degree of a divisor is now a real number. And any real number appears. So you are really in a totally new territory, okay, where the degree of divisor is no longer an integer. But of course, to an operator algebraist, this is very familiar, because this is for Neumann's notion of dimension, which is no longer an integer, but which is a real number. Okay, so we are not put off by this, on the opposite. Okay, where okay, so and you have a notion of principal divisor. I mean, all of this is routine once you have the right formalism. Okay, so there is a notion of principal divisor and so on. Okay, there is the notion of so there is the fact that when you take, you know, the degree of the principal divisor is 0. All of that can be checked. It's rather elementary. But what is less elementary is the following: is that then you have a first theorem which corresponds, if you want, to the Jacobian. So this theorem tells you that you have an invariant, in fact, for divisors, and it's an invariant which has values in the group which is z over p minus 1z. So it's a non-trivial invariant that you get, okay, for divisors. And then we have a theorem that the map which is combining the degree with this invariant chi is in fact a group isomorphism of the divisor classes with the product of R by this finite group, Z modulo p minus 1z. Okay, and then what we did with Katya was to investigate the, you see, the theory of elliptic functions. We investigate the theory of the theta functions, because to construct elliptic functions, you need theta functions. So we did the analog of theta functions and on this R plus star divided by P to the Z. You see, I mean, the whole beauty is that it's a very non-trivial structure, even though it's R plus star divided by P to the Z, so it's a circle of length log P. It has a very non-trivial structure. Okay, so then we could imitate the formulas that people use in order to construct theta functions. We imitated them by using the language, if you want, of tropical geometry, which allows you to translate a formula which is written multiplicatively into something additive, but you replace, if you want, the sum by the maximum. And so then we got a theorem very much like for elliptic functions, namely that the corresponding elliptic functions in our theory can be written in terms of theta functions. Okay, so that was the basic theorem. And moreover, what we found, which is crucial for the Riemann-Roch theorem in that setup, what we found is that if you want, there is a natural filtration of the elliptic functions by means of the p-adic valuation. Namely, as the whole story is based on a given prime, it's given that these denominators p to the n. So there is, if you want, a link, of course, with p-adic numbers. And then what happens is that when you filter by this p-adic notion, what you find is that even though the space of sections for a given divisor is sort of infinite dimensional in the naive sense, in fact, it has this filtration formed by objects which are finite dimensional, okay, which are finite dimensional in the sense that they only depend on finitely many constants. So then we defined, following the idea of von Neumann, the continuous dimension, the real valued dimension, by taking the limit of the topological dimension of the space of solutions, but divided by p to the n. So this is strictly analogous to the von Neumann dimensions, okay? And then we proved the Riemann-Roch formula, Riemann-Roch theorem, which told us that, you see, it would have been impossible to have a Riemann-Roch formula with a real valued degree without using the von Neumann dimensions. This would have been strictly impossible, okay? So then we have this Riemann-Roch theorem. And so the Riemann-Roch formula is extremely simple in that case because it's an elliptic curve. So there is the genus doesn't enter in the formula. Okay, so we were quite happy with this, but okay, it was really a warming up, okay? And it was a warming up, it was still one-dimensional. So in a way, we didn't have to worry about H1 because we could use third duality, as an implicit beta, and replace, if you want, the H1 of D by H0 of minus D. So this was a little bit of cheating. And then we tried to come back to the original stuff, which is to imitate Matuc-Tate. And when you want to imitate Matuc-Tate, you see, Matuc-Tate is incredibly simple to state because you have a Riemann-Roch formula. If you have a Riemann-Roch formula of this form, you are done because what you want to prove is the negativity of this. This is equivalent to RH. And Grothendieck added to the Matuc-Tate paper, what they say, Matuc and Tate, is that they missed the boat. But Grothendieck got into the boat. And he found the missing trick. And the missing trick is that once you have this Riemann-Roch formula, you are done because you can easily control the dimension of H0 and the dimension of H2. This is not a problem. And then minus dimension of H1 is automatically a negative number. So you are done, okay? So that's what we are trying to do with Katia, okay? To imitate this. Of course, this would require a Riemann-Roch formula, not for the periodic orbit, not for the curve itself, but for the square of the curve, okay? So, and there, we were like a horse in front of a big, obstacle. And what we did with Katia, we wrote a long paper trying to develop homological algebra with characteristic 1, okay? And what we met really a huge difficulty, which was what would be the suitable definition of H1. And it is that difficulty that actually led us to absolute algebraic geometry. And I will finish my talk to explain that in a few words. But this absolute algebraic geometry will be, if you want, the essence of the talk of Katia and of what the joint work that we did for Riemann-Roch theorem, but it will be a Riemann-Roch theorem for the integers. Okay. So the way this absolute algebraic geometry appeared, it appeared, if you want, because there was a flurry of different attempts by many people to define what is this field with one element. Okay, many people, it's good. That's what we need in mathematics. We need imagination. After all, we have to remember that complex numbers were found by Bombelli, and Bombelli had this completely crazy idea, which was più di meno. He was using plus, minus, and he had this completely crazy idea, plus de moins, più di meno. And this meant, of course, the number I, Okay, so that's what we need. We need a lot of attempts and so on, but we need also to be very tough with these attempts, okay? And what we stumbled on with Katia was a notion which actually embodies all these different attempts in one notion. And what is the big step? The big step is the following. The big step is to think functorially. So what I ask you in order to understand that is to make the following effort. I give you an abelian group. Okay, let's call it A. But now let's forget about A as a set with an addition and so on. No, I want to use A to define a functor. And this functor is a functor which, if I am given a set, okay, will associate to this set the divisors on X with values in A as a set. Okay, you have to take pointed sets, but I mean, this is a detail. Okay, so now we replace an abelian group by a functor. It's a functor from pointed sets, let's say finite, it's enough, from finite pointed sets to sets, pointed sets, okay? That's it. Now it's an exercise to show that you don't lose anything if you do that. Then namely that you can recover the group operation from that, okay? But you get many more stuff. And in particular, the identity functor is not coming from a group, okay? And now, so the theorem is that the category of abelian groups, or in fact abelian monoids, embeds faithfully, okay? In other words, you don't get more morphisms in the category of such functors. Now, such functors, if you want, are called gamma sets, but very soon they will be called S modules, because the identity functor, we call it S. And eventually it will correspond to the sphere spectrum, okay? But we call it S. Now, the beauty of this theory is, okay, of course you get a symmetric closed monoidal category. I mean, you know, you have all the, and the morphisms, of course, between two such functors are given by natural transformations. And so, I mean, you get a very nice category, very controllable. You can work out with it. I mean, you know, it's not abstract homotopy theory. It's something very concrete, which goes back, in fact, to Graham-Siegel. And now all the various attempts that people had done to define F1, they all turn out to correspond to special cases of this story. Okay, the monoids, the algebraic monads of Durov, the semi-rings. I mean, all of that, they fit perfectly inside. So we were happy with that. And then it turned out, if you want, that the identity functor corresponds to the sphere spectrum. And the essence of this story is the following, is that, you see, what we wanted with Katia was to do homological algebra. Of course, that was crucial. Now, the true understanding of homological algebra is due to Dolkan and Quillen. And what is it? It tells you that when you do homological algebra, in fact, you shouldn't do it with complexes, you know, and spectral sequence and all that. No, what you have to think, in the terms in which you have to think is different. You have to think in terms of homotopy theory. And what is the link between ordinary homological algebra and homotopy theory is given by the Dolkan correspondence. So the Dolkan correspondence, what it does, if you want, it takes the category of abelian groups and so on, and it makes it simplicial. So what it does, if you want, it replaces this category by the categories that you obtain by making it simplicial. Okay. In other words, it's a very simple thing. It's functors from the etc. etc. Okay. Now the beauty of what we are doing with Katia is that when we take the category of gamma sets or S module and you make it simplicial, you obtain a category which is well known to homotopy theorists, which is the central topic of a book by Dundas, Goodwillie, and McCarthy, which is central in algebraic case theory. Okay, so what we knew from the start with Katia is that then, if you want, we won't have to do all this job of redeveloping homological algebra from scratch for the theories that we have. It has already been done, okay, except for one thing, that it has been done in a way which is too brutal. Too brutal. Why? Because they follow the precepts of Quillen, okay? And by following the precepts of Quillen, they find a model category and so on. And immediately they transform any space into a fibrant space. And this is extremely expensive at the homotopy level. It means, like, you know, taking infinite loop space and so on, which for an analyst is a nightmare. Not only that, but it transforms something which a priori is not a group into a group by inserting artificially the minus. And this is not what we want. This is not what we want. So we have been forced with Katia to refine, if you want, what the homotopy theorists do, and this is what Katia will talk about, and to refine it in such a way that precisely, if you want, all these nuances and so on are kept. They are there. They are there immediately from the construction. And so let me show you the last two slides. So, well, we found this on, we found that the BC system was in fact the VIT construction of the algebraic closure of S, but I don't want to involve in that. I just want to finish to prepare for the talk of Katia by telling you that, of course, you know, when you have this Rosetta Stone, the most obvious question is, what is the analog of Riemann-Roch for Z? Okay, and so, I mean, so Katia will talk about that, but I don't resist the temptation of saying one thing, okay, which is one thing which sort of, you know, because you can say, oh, I have a Riemann-Roch for Z. Okay, fine. What did you learn about the integers from this theorem? Okay. Now, it turns out that Manin had a very provocative question at a point, which was to say that integers are like polynomials, you know, because they are genus 0, you know, and so on and so forth. Okay. And this is what we found with Katia by proving our Riemann-Roch formula. What we found is that they are indeed of genus 0, and because they are polynomials. So the integers appear as polynomials over the sphere spectrum with the generator, which is -2. In other words, any integer can be uniquely written as the sum of powers of -2 with coefficients 0 and 1. Okay. That's a known fact, but it takes its life in this Riemann-Roch formula that we shall hear about. Okay, thank you.